So so when I was a graduate student, I was watching Browder present this marvelous theory where he could construct in dimensions greater than 4, of course, but still, and he was assuming simply connected. He could construct all smooth manifolds and classify them up to diffeomorphism. This is simply connected dimensions 5, 6, 7 in terms of homotopy data and various constructions, surgery, and stuff like that. But as I was telling you before, we start stating the hypothesis and the theorem, and the theorem would take to about here in about 20 minutes, and then you start the proof, and that would take the rest of the hour. You wouldn't get halfway through the proof, and the next day you'd come in, the next class, and start again. And it was sort of clearly fantastic, but it was not understandable in terms of, you know, math. So my thing turned out to be to try to just reformulate it, and so I'll tell you about the reformulation. And
are you being modest when you say that you just reformulated it?
Yeah, a little bit.
Okay.
No, I had to. It's like going into a ring with a tiger, and you know we bit each other, and I bit him in the neck, you know, something like that. But just reformulate. No, it's just. It's a reformulation. I don't know. I like to think of it as a reformulation. It's a reformulation. Yeah, but no. And I'll give the idea, and I'll tell you when this happened. But then the next thing that happened, and I'm trying to reformulate it, and I got something that was looking pretty good, and there were 2 stages of it, and. The first stage was beautiful, it worked very nicely, and then I got to a second stage, and these exotic spheres were coming up, and you know, and so I had Milner there, so I went to Milner, the man who created exotic spheres, and I was showing him this, and he said, also I was tired of being a graduate student, I wanted to get out of there and write a thesis. Anyway, it's another story. Milner looked at it and said, well, why don't you just forget smooth manifolds and do it for piecewise linear manifolds? Then the exotic sphere step just goes away, and the first step, which is nice, I mean, you didn't say all that, you didn't say so many words, and then it's like you change the problem to fit the naturality of what you're observing, so to speak. Yeah, that's. And when I said, oh, I said, yeah, thank you. And I said, I don't like PO manifolds. You know? You know, you like nice, smooth things, you know. and then I, you know, I thought about it. And well, wait a minute, this is. I was kind of depressed. I didn't have anything there, and then I realized, well, wait a minute. If I follow a suggestion, it works perfectly. You know, you get a complete statement, and I'll tell you the statement, and then. The next day, I was the Dinkelspiel champion at the time. We had a long table in the common room and we played with ghost stones. Mm-hmm. Ralph Fox didn't like it because we cracked his ghost stones. And the champion could be challenged, but he didn't have to play if he didn't feel like it. So Browder came up and he said he wanted to play me, you know, challenge. And I said, I don't feel like it. I don't have, you know, I was sort of feeling down because I didn't have anything, you know. And then we're sitting over there talking, and he said, well, I've got this, told him about what the reformulation of Milner, and he said, I said, well, is this a good thing to work on for my thesis? And he said, well, that is your thesis. I said, okay, I'll play, you know. I don't remember who won, but anyway. Anyway, so so we're going to formulate the problem like this. Suppose you want to, you're in this simply connected dimension 5, 6, 7, because there's, I'm explaining in terms of this Poincare duality picture why, which we were talking about earlier today, why you need those hypotheses. And then you're going to consider manifolds. Not, and they're going to be piecewise linear. So this means they have charts in Euclidean space, so the overlap maps are piecewise linear homeomorphisms. After some subdivision, it's a simplicial homeomorphism. Okay? And then you can develop many of the things for smooth manifolds. And then what was known at the time is that piecewise linear manifold is a good thing to base smooth manifolds on. You can consider all the differentiable structures on a given compatible with the underlying piecewise differentiable or linear manifold. And for the spheres, these were the famous Milnor exotic spheres. They start in dimension 7. Every sphere has a unique smooth structure up to dimension 7 if you give the underlying piecewise linear structure. And then you have 28, and Z2, Z2, 0. And they're finite. And then that theory enlarged to, for general piecewise linear manifolds, they may not be smoothable. Carrère gave an example of dimension 10 of a piecewise linear manifold that could not be smooth. But if they are smoothable, there are only finitely many smoothings. And they're actually a torsor of a finite abelian group. This was all very fascinating. What are these finite groups and so on? How do you classify them? So that's why I was trying to understand Browder's theory and reformulate it to classify smooth manifolds. And it turns out that finite group is more or less equivalent to knowing these famous homotopy groups of spheres, which is hard to know and still unknown. This is 60 or 50 years later. 55. Anyway, so that's the story. So the piecewise linear manifolds basically are like smooth manifolds, except you don't know which ones are smoothable, and if they are, which ones, how many there are, but it's all finite. All the obstructions are all finite, so you have some grasp on that. Anyway, so and they have enough geometry in them, you can do everything, transversality and constructions. And in dimension 4, they're the same as smooth manifolds up to including 6. So they're the same. So 4 manifolds, all the Donaldson theory, Sullivan theory, of smooth manifold theory are the same as for PL manifolds. So anyway, I'm not going to classify them in dimension 4 because I would also be classifying smooth manifolds in dimension 4, and that they're still not classified, even with the Donaldson Sullivan theory just gives you a lower bound saying there's quite a few of them. So anyway, and this theory was so successful it kind of almost died out in the 70s. It solved the problems in this surgery theory. But I'm just jumping in on and reformulating. So, okay, so the idea is, okay, so then the idea is to classify them. How are you going to classify them? So you're going to kind of fix the. You kind of fix the homotopy type. You're going to fix the homotopy type. So this will be something that the top homology is Z and satisfies perfunctory duality. That was Browder's idea to emphasize that concept. And then he had a whole big machine for building the smooth manifolds, and it worked for PL manifolds too, in the homotopy type. And but let's dispense with that machine. Let's suppose we've already done it, and we've got a manifold, and we've got some manifolds in this homotopy type. So these are different manifolds that are homotopy equivalent to that. And so actually, the more precise thing is let's let X refer to the homotopy type and say a manifold in the homotopy type means the homotopy equivalence of some closed manifold to the homotopy type that satisfies perfunctory duality. And then two such things would be regarded as equivalent if there's an isomorphism here, namely piecewise linear homeomorphism, so that this diagram commutes up to homotopy. This is how you define moduli space and Teichmüller space for Riemann surfaces. You get the topological surface here, you get the Riemann surface here, when you have a conformal isomorphism here, so this diagram is homotopic commutative. That defines the type number space for Riemann surfaces. And this is called the structure set of X. Structure set of X. And so we want to classify the manifolds in the structure set. Okay, so and the idea is the following. So you, now, let me just, before I, well, okay, I'll do it in order. Okay, so the idea is the following. You think of a manifold as like has a cell decomposition, but via handles. This is the idea that Smale used to prove his Poincare conjecture. These are one handles, and then kind of an igloo sitting on that would be like a two handle, and then you can go on up like that. You build the whole manifold. So you get one from a Morse function if you want, a handle decomposition. It's like a cell decomposition, but geometric, manifoldized, right? Then the idea is to take the geometric idea is to take one manifold, or M1, and then consider any other manifolds, or M naught, say, just M, say, any other manifold M prime, and take this homotopy equivalence. And let's directly try to homotop it to a piecewise linear homeomorphism. Okay, so well, let's start here. Take a point, the core disk of this zero handle, and then move this map to make it transversal. This is a homotopy equivalence. So you get various points in the preimage, plus, minus, plus. This has degree 1, it's a homotopy equivalent, so the algebraic sum is 1. So I've drawn that way. This is a plus, and these two minuses. We can kind of draw a path between them, and you can physically make a homotopy. You sort of come out from the board here and put this path as a kind of coordinate into M cross I, and you adjust the map. And you make a homotopy to cancel these two preimages. It's sort of like the thing is folding over like that, and you're pushing the fold out. You kind of make a construction of the product. Okay, and then so then you get it, so the preimage of this, the neighborhood of this point is just one point, and it's transversal, so it's like, we could think of it on the whole ball here, the preimage is just a ball, and the map is a PL homeomorphism on that ball. Okay, I haven't lied very little, and that's essentially complete proof. Then we take the one handle, the core disk of the one handle. This picture is. This is picture of your M naught, your M. So I'm pulling back that. Now I pull back the core disk of the core of this one handle. I'll get something. There's not many choices for a one manifold. I have to have something here. This is a diffeomorphism, PL homeomorphism here, so I get 2 points here. And then there can be other things here. And now this is all mapped to there. Well, you do a similar argument to do kind of a surgery to make this connected. It's not too hard to make this preimage be one connected arc, and then again, make this map from an arc to an arc. It's a PL homeomorphism, and you can do the one handles. This is where it helps that you're not in dimension 3. If you were in dimension 3, this could be knotted, and then when you do that connected sum, it would still be knotted, and then you would. Oh yeah, and then, well, okay, I kind of skipped a step. But in your entire dimensions, this isn't knotted. Then you get a PL homeomorphism here. And now, what is true is, when you haven't created any fundamental group or spurious knotting or something, The complement is also a homotopy equivalence. Now, I forgot to mention that before. See, the map on this part is a homeomorphism. And then the map on the rest, that's the global thing, is a homotopy equivalence, has to also be a homotopy equivalence. It's easy to show it's a homology isomorphism. In the case when everything is simply connected, controlling things, it'll be a homotopy equivalence. But in dimension 3, that knot would have created the complement of knot as the homology of the circle, but it's not homotopy equivalent to the circle. So this doesn't work literally in dimension 3 because of that. Anytime you get codimension 2 things, you're in trouble with that from that point of view. But we're not in codimension 2. So anyway, you fix it up to be on the one skeleton, and then now you get this igloo. You get this 2-cell thickened up. It's a PL homeomorphism on the boundary. I'll say isomorphism and homotopy equivalent, okay? This sort of works in whatever category where the tools work. So you have an igloo sitting on this, you make it transversal, and you get the surface back here. They'll have a boundary, and there'll be some kind of surface, and this has a framing, so you have a framing here. And then you start trying to do the surgery. So what you want to do is see, this is mapping to a disk. See, the igloo over here is like a disk. So you have a surface mapping to a disk. So all this homologies goes to 0 on the disk. So you want to take a circle here, and you want to do a surgery, and cut it out, cut out this circle, and glue in this other little thing here. And there's an obstruction, there's framings going on here in the normal direction, and so there's some kind of framing issue to make this homotopy, which I can't explain now, I don't remember. But there's kind of a little Z2 obstruction to make this work. And well, it turns out it's a quadratic function on the homology of this. And a quadratic function on the homology, Z2 homology, is actually an object that has an invariant, an ARF invariant. There are 2 isomorphism classes given the rank. The trivial one, where you can do the surgery, and the non-trivial one, where you can't. And so you have to associate to this 2-cell the ARF invariant of the framing issues that appear here. And it's a geometric property of this homotopy equivalence.
So that's occurring in all dimensions, not just the middle dimension?
And so what we got is, when we started the process, in degree 0, and there was no obstruction, and then we were in degree 1, and there was no obstruction, and then when we get to degree 2, we get a Z mod 2. We could have had a Z obstruction here. If this degree were not 1, there would have been an obstruction, but one could have Z there. Anyway, so on each cell, we get an element Z2, which is the obstruction to doing surgery on the pre-image to make it a disk. But if we could get it down to a disk, then we have a map from a disk to a disk, which is a PL homeomorphism on the boundary, and you can make that be a PL homeomorphism on the interior, and then you would go over one more handle. I'll come back to dimension 2. We have to process this a little more. And then we go to dimension 3, go to the 3 handle. Now, actually, it's sort of interesting. If you're in dimension 5, let's see. Well, no, it's not the right thing to say. Sorry. Yeah, now, as you go up in dimension now, this way of looking at it is not quite good enough because now the codimension starts getting small. So in dimension 5, I would have the codimension 2 thing would be true. So I have to sort of change the formulation, but it turns out you don't lose the problem by crossing this manifold with a disk and crossing with the identity, and think of the manifolds with boundary. turns out the obstructions still work the same way, and you can make the codimension be big. This is because you're in this higher dimension. Anyway, that's a technical step. I'm just kidding. Anyway, this is sort of the idea. So I guess, but let's suppose this is not 5. This is big dimensional, so I can discuss at least 4 of the dimensions. So there's a Z2 in dimension 2. Then when you get to 3, the pre-image is this odd dimensional manifold. Mapping, this is the 3 manifold, the frame, and it's mapping onto this 3 ball, the diffeomorphism, isomorphism of the boundary. And now the surgery was done in this famous Ktheory paper. So you fight with the 1 cycles and linking and so on, and the surgery can always be done. So you always can complete the surgery, get a disk, and then make it appeal homomorphism, and then finally we get to dimension 4. And then the whole thing, we're going to discuss 4, and then the whole thing is just going to cycle again. 5, 6, 7, 8 are the same as 1, 2, 3, 4. It's periodic, the discussion. We go to dimension 4, you see we've done 3, and we go to dimension 4, and now we get a 4-manifold pre-image here, and again it's got middle dimensional homology. Now you have a quadratic form on the homology, and when you diagonalize it over the reals, it's subtle pluses and minuses, so it has a signature. And the signature is the obstruction to doing this process. Actually, it's kind of interesting. All the intersection numbers are even because of all this framing. These things are all going to 0. And that gives you the information that this the framing is the intersection numbers, self-intersection numbers are even. And so actually the signature of this thing here is actually divisible by 8. So the real obstruction is sigma divided by 8 that you attach to this force field. So this is all just, if you're a graduate student at Princeton in those years, these are just what you read in the papers, Premier Milner's paper. So it's really cool stuff and so on, but like that was what my oral exam was about.
So when you say you attach these to those cells, are you building a co-cycle?
Yeah, now I'm going to get to that point, yeah. So, I mean, these are like, call these obstruction cochains. If all these numbers kept vanishing, I could just keep doing this process and I would win, okay? Now we want these numbers to be part of some little algebraic structure. But this is side of the idea. And then I have to explain, I would have had to explain why I could stabilize the dimension and not get into this knotted phenomenon. That's another point that I'm missing. But anyway, so what you're getting is C is dimension 4, and then it just repeats again. And then now so you know what, in being a graduate student with Steenrod teaching you algebraic topology and so on, you had to learn about obstruction theory, and then you find out that, so there's this, what I'm going to claim is that when you're at some, so I used to draw this picture, pre-image up to some point. This is all good for here, and then I have cells, thickened handles added onto here, and then I take their pre-images and I get some stuff in here, like that. And this is the stuff I want to surgery away inside there. And if I can do the surgery, I can make this look like a homeomorphism and have it be part of the good part. Right? So that's the idea. And now so this is assigning to each cell a number, either in Z2 if you're in this dimension, 0 if you're in this dimension, that's no problem, and Z in those dimensions. And the Z is like a signature divided by 8. It's part of some of the details of the theory. Then,
and these are the RF invariant and signature mod 8 of the pre-image?
Yeah, of the relative pre-image.
Relative.
On the sphere.
There's isomorphism on the boundary. And it's like there's isomorphism in this thing with boundary of sphere, with the disk with boundary of sphere. So you could glue them together if you wanted to have a closed thing to talk about it. All right, then you prove, lemma 1 or 0 of obstruction theory. Lemma 1 or 0 is that the cochain is a cocycle. Namely, you think of this as cell decomposition, that when you look at all the boundary pieces, there's a 2-cell coming down here. You look at all of the boundary pieces, the sum of those things are 0 because you just do the pre-image again and you get some kind of cobordism connecting all these problems, and then the signatures of cobordism invariant, so the sum has to be 0. That means more subtle for the Arf invariant, same idea. Okay? So it's a cocycle. So this get this cocycle, so we get a kind of theorem. Well, we get a theorem that there is, well, here's the theorem. This is one. I told Mr. Browder, he said, that's your thesis. Okay. And I said, okay, I'll play with you. I had a headache and it went away immediately. Sort of incredible. You had these tension headaches or something? I said, I don't have anything. I want to get out of this place. Theorem. So there exists obstruction theory for deforming a homotopy equivalence to the PL homeomorphism. There exists a series of obstructions in HI of X with coefficients in PI, are those names of group, where PI is this string of groups here. So with every 4K plus 2, there's a Z2 obstruction, and in 4K, there's a Z obstruction, and in the odds, there are no obstructions. Okay, so that was it. So that was my thesis, and my thesis defense. This goddamn Steenrod at the thesis defense said, well, it's all very well and good to have a theory, but how do you compute the obstructions? I said, what? I sort of thought, what? Because there was an analogous obstruction theory for deforming, for the smoothing theory, the smoothing theory had obstructions with coefficients in the millimeter exotic spheres. Nobody asked how to compute those obstructions. They were just relieved there was some obstruction theory. So here I'm giving them an obstruction theory where I explicitly tell them the groups, and they want me to compute the obstructions. And anyway, that was a very good question. It also made me decide that oral exams should be adversary. They shouldn't just be all your friends come and watch you give a talk on your thesis. Because some of the people in the audience might know something about what you're talking about, and they might ask a question. And it turned out that's what guided my next research for a long time. It was very important. It turns out this happens to be one of the very few obstructions theories for which you can compute the obstructions. But I would have stopped here, because this is already better than the previous one, which was very, very beautiful, I thought. Okay, so I was kind of.
So do you think did the question about computing mean identify it with some other known thing, or did it mean do examples?
I have no idea what it meant, but it was sort of like do something more than just state it exists. Well, so before I. So the next thing, kind of at the same time, actually, and it turned out when I wrote the thesis, it turned out I could do a little bit more. You could say you have this X and this M and this homotopy equivalent. You could say that this pair corresponded to a map of X into some universal space whose homotopy groups, say I'll call it U. Homotopy groups of U were these groups, 0Z2, 0Z, 0Z2, 0Z. And getting these two, in other words, this thing corresponded to homotopic classes of maps into this universal space. So you could prove that. In other words, when you have an obstruction theory and you have enough material, something called the Brown representation theorem, and you could use that to show that there really exists a space that embodies all these obstructions. I mean, it's just a kind of formal thing, but useful. Because then we could say, well, okay. So I thought, well.
So being a question. So it means that if that were equivalent to a PL homeomorphism, then it would go to be a contractible map.
Null homotopy.
It would be null homotopy. Null homotopy.
No, so let's see it. Sorry. The maps into this act on this set. So,
so it's like
sorry.
a fiber.
The difference between two. So if you want to, so this composition will be a homotopy equivalence, and I'm trying to homotop it to an isomorphism.
Right.
And I get this obstruction theory. So it's just the obstruction theory of homotopping this map to zero. So I just stayed there.
Got it. Okay.
All right. And in fact, this is a group also. So this is the torsor of a group, this set of manifold structures. Okay. So then, it's just sort of formal that there exists a space. So it's really nice to have smart graduate students around. So I went to my friend George Cook and I said, well, wait a minute now. There's one space that this might be, just the product. This could be a KZ22 cross KZ4 cross KZ26. Just, these are the spaces that have one homotopy group, blah, and dimension blah, on the urban plane spaces. This space will have the product homotopy group, so that'll be a space. So I went to my friend George Cook. I said, George, when is a space when is a space with given homotopy groups equal to the product of on-urban plane spaces with those same homotopy groups? And without hesitation, he answered, well, Dennis, if and only if the Hurewicz homomorphism is an injection onto a direct summand. So we got it, So what does that mean? You have the pi I of x, u maps to hi of u. And if that's an injection onto a direct summand, that means there's a map back so that this composition is the identity. Then you can build a cohomology class with values here, like cohomology is hom of homology into the A with some kernel it maps onto. So if you had a map like this, you could build a cohomology class Q in HI with coefficients in pi I of U. And then that cohomology class would be induced by a map of U into the K pi I of U, comma I. And then you could take the product of those classes, product of those maps, and that would be an isomorphism on homotopy groups, so it would be a homotopy equivalence. Bingo. So it was easy to prove what he said, but he knew the answer, without hesitation. So I went up into the classroom, laid on the table like this. Okay, I wanted to, just take the definition. I'm going to map. I take the I don't know the space. I don't know its homology, but I can make a picture of a homology class. A homology class is something like a manifold mapping into the space, right? With singularities or something. Right, Razana? Can you make a picture of a homology class? Private joke. Yeah? You have to have a picture of a homology class. And I thought, well, wait a minute. What if? So I want to find a manifold of dimension I mapping into here to represent this homology class, and then somehow from this map get an element in the homotopy group. Oh well, there's this theory of Tom Steenrod's problem, which homology classes and spaces can be represented by manifolds. I talk about that a lot. This is why I talk about it a lot. We can represent any multiple. So, well, these Z ones, that's not too bad. If I could get something there, but It'd just be a multiple, wouldn't be a split injection. And then, but I remember Tom said that any homology class at the prime 2 can be represented by manifolds. That means you can multiply it by an odd integer and you can find a manifold. So I said, okay, I can't hit that guy, but I can hit an odd multiple. Oh, wait a minute. So, but in one of the groups I'm trying to do is Z mod 2, so an odd multiple is okay. If I multiply something by an odd multiple, that's still okay. And so, and then map, what is the map into, this is a map into U. What does it mean? It's a surgery problem, and sets up a surgery problem, and I can look at the surgery obstruction. Oh, if it's in the right dimension, 4k plus 2, that's an element in Z2, so I had it. That was it. So you could split it, and then you could do it for these Z's if you went ahead and if you went ahead and took algebraic topology and introduced a half into it, which is something you can do, we knew how to do that, and create another space, which is called localizing away from 2, then this space would be like that, and then everything in here could be, the odd multiples don't do anything when you have a half in it. And so you could get everything. So this whole space, my whole space, was a product of Oliver McLean spaces at the prime 2. Now I've lied slightly. The 8 is a 16 in dimension 4, and there's one little twist right here, but I don't have time to talk about that. There is one slight twist. Except for that, you can analyze that. So this is kind of what went into my actual thesis. And now there was a, so that means, so basically you've got some, so if you ignore odd torsion, so if we ignore odd torsion, I think the title of this talk is how K-theory classifies manifolds for odd primes. Something. What's the title of this talk?
I already forgot it.
Well, at some point when you read the title, I'll ask you in a minute.
Okay.
Because this is like background. So what it's sort of saying is that you can think of a map into this space as just a bunch of like characteristic classes, and then this thing there. Manifolds will have, the difference between two manifolds will have these characteristic classes, and they vanish if and only if the two manifold structures are equal. So you have a kind of calculation of the obstructions, an a priori calculation. And another interesting feature of this was, this became the motivation, is that if this is a homeomorphism, we would like to know that all these obstructions vanish, because then we could homotop it to a piecewise linear homeomorphism. And that was a famous problem in those days called the Haupt-Vermutung for manifolds. And if two manifolds are homeomorphic, are they piecewise linearly homomorphic? And so these obstructions involved a surgery consideration, and it turned out Novikov had proven that Pontryagin classes are topological invariants, and those Pontryagin classes can be used to compute that signature. And so there was a connection between those things, and you could actually take his proof. If you had the homeomorphism, his proof was a way of creating transversality. And you could take this manifold and pull it back. Before I was pulling it back, I took the homotop equivalent and pulled it back, and I got this extra thing, and I took the surgery obstruction. But when it's a homeomorphism, Novikov had a way of pulling it back via homeomorphism, and then these two manifolds were, actually it was a little bit subtle, but they're open in the neighborhoods of each with proper homotopy equivalent. Anyway, they would have the same signature, and that's how we got the invariance of Pontryagin classes. But in this case, it gave me that all of these obstructions were 0. So if a manifold didn't have any odd torsion, this proved that all my obstructions for the previous theory, when you applied them to a homeomorphism, were zero. Now, there's an important point here that, you see, when you do obstruction theory, if one obstruction is zero, you go on to the next step, but you use some deformation to go on to the next step. And then you meet the next obstruction. That obstruction depends not only on what you started with, but also the deformation. Now, if you were proceeding like that, as soon as you touch this homeomorphism and moved it to kill one of the obstructions, it would only be a homotopy equivalence on the rest of the space. And so you've lost your hypothesis. So what you have to know is that you're doing this process, and you have to know that when you meet an obstruction, it's a priori defined and is zero for some reason. And the idea is that the obstruction is going to be at a cell like this, and Tom's argument gave a kind of manifold running through this, that sort of goes through the cell that represents the homology. So when you finally get up to here and you take this surgery obstruction here, well, you could say, oh, I could have done this before I started the whole process and done the transversal pre-image, and a surgery obstruction, which is kind of spread over the manifold, has just been oozed up to the top here, but they're the same thing. So the a priori calculation, if you knew that were zero, would show that when you arrive here, this obstruction is zero. Okay, so you have to have an a priori, so it's like Stephen Roth's question, you have to have an a priori obstruction calculation of the obstructions before you get there. So the only way I could think of doing that is give a homological, extend all these cells to the essential cells that define the homology to cycles for which you can define the surgery obstruction. Or manifolds you can do it for. So at the prime 2, we're good. Now it turns out at odd primes, there are obstructions. So Tom gave an example of a 7-dimensional homology class in the space that has 3 torsion, and any there's no manifold mapping in to hit that class. So there's no way to a priori catch that obstruction in this way. Now the other part of this obstruction theory is that, well, you go successfully up and you meet some obstruction. Well, you can back up. In fact, you have to back up a little bit to get, if you just go right here and hit it, you get obstruction cochain. Back up one step and go forward again, you get a cohomologous cochain. And if the cohomology class is zero, then you can back up and get zero and then go forward. Or if you can back up more and try to change the cohomology class, and says, well, okay, what's the ambiguity of the obstruction? Maybe there's enough ambiguity so that I can kill it by backing up more. Well, that kind of thing is not really done. You analyze an arbitrary, it's like general obstruction theory by going back and understand that sort of. But since I didn't know very much, I didn't know that you could try thinking about this. So you could still think about it. And then I'm still trying to answer Stephen Roth's question, how do you compute these obstructions? So it's got this labyrinth idea, right? All right, so
you know how to build obstruction.
what?
No, you know how to build obstruction on this process.
Yeah, you were here when I talked about the transversality, right?
Yeah.
I mean, the obstructions are only defined when you're sort of doing skeleton by skeleton, and then you get to want to do the next step, and then you meet obstructions. And
what is it to compute?
if they're non-zero, they're non-zero. But you might back way down and start going up another route, and maybe you can get further. So that's the way obstruction theory is. It's usually you only use it when you can get the cohomology groups to be zero or something like that. So all these zeros here are helpful, and if the space is, so we already have a pretty good theorem here now, if using Novikov's argument, and Tom's seeing at the prime 2, that if the space has no odd torsion in its cohomology, then the complementum is true, except there's this little thing here is an additional, my argument only shows it has order 2. And it turned out later, Kirby Sieberman built examples based on this. Yeah. So that little thing there is obstructing that Haferlute. It turns out in the end to be the only obstruction. That little thing there. And if you just work with top manifolds, this thing really would be a product, and this twisting isn't there. Anyway, that's another point. So, okay, now what's the title of this talk today?
It is How Complex K-Theory Classifies Manifolds at Odd Primes.
Right. So this is the story. It's like over at the prime 2, essentially. I can't get this one to be 0. It only has order 2 for homeomorphism. But, you know, if you don't care about this Haferlute problem, you just say homotopy closure classification. Even with this here, this gives an answer at the prime 2. And this is the way BSO looks up to the 4 skeleton. Yeah. All right, so all right, so now let's see. So what happened?
So Dennis?
Yeah.
So just to recapitulate, part of what you want to do is have your obstructions rigid so that the complements are always homeomorphisms when you do the surgery, so that you don't leave the world of homeomorphisms.
No. I mean, that's impossible. This theory is about deforming homotopy equivalences.
Right, but if you started with a homeomorphism, that's...
No, I know. And so the only way you can, what I did, and answer Steve Ron's question, is to give a priori computations of the essentially rigid part of the obstructions.
Okay.
That's what the title means, but at the prime 2, I've done it already, because I analyzed the space. At odd primes, you have to analyze. And even if you analyze the space, it's not clear a priori that given space, you can find the essentially rigid part of the obstructions and express them in some way. I didn't know any of that. Turns out the only space for which you could do that sort of thing, which is non-trivial, is the one we have. So it was a great piece of luck. It has to do with the miracles of Ktheory and stuff. Okay, so that's the next part. Okay, so basically we have this obstruction theory, and we understand it at the prime 2. It's just essentially trivial with one little twist, which has big significance, actually. Because, you know, this is dimension 4. It's all related to what's going on with lots of things. Okay, so then this morning, which was kind of background, we were talking about homology theories, and so there are a bunch of invariants. I mean, I take my homotopy equivalence, and I have my homotopy equivalence, and I can take a manifold back here, and any manifold back here, and take its pre-image, and I'll get a degree 1 map, and then it turns out from this manifold to this manifold, and it turns out if you draw a picture of the homology, that's what I did over there, this homology looks like a copy of this homology plus another almost copy of something satisfying parametric duality, except it doesn't have the bottom and the top group. And this is direct sum. So this is the way a degree 1 map between closed manifolds look. The domain is a copy of the range, direct sum, another copy. Both pieces satisfy Poincare duality. And the surgery obstruction is sort of living in the middle dimension here. It's either the signature or this Arf invariant of this kernel. That's the signature obstruction. So that's sort of a picture of the homology. And then that's if you do closed manifolds, but it turns out you can do manifolds, what I call ZN manifolds. You can take manifolds which have, you can take like, here's a Z3 manifold. You have 3 isomorphic boundary components, and you just manifold boundary with 3 isomorphic boundary components, and you just glue them together by the isomorphisms, and then you get this, and you get three things coming in. Okay, and you do that, and then you see if this glued up thing is mapping into your space. I'll just draw a drawing like that. So you have 4 things coming in here. This is, and you have n things coming in here. So this is a picture of a Zn homology class. Okay, because it's a cycle whose it's a chain whose boundary is divisible by n. So if you reduce mod n, it's 0. And then you can still do this, the transversality, and you get something back here with the 4 things coming in here. And then you kind of open this up and study how it varies under transversality, and you get, it's not well defined, the surgery obstruction, but it varies by the same thing as you form here. So if you reduce the surgery obstruction mod n, it's well defined. Okay, so this is a bunch of a priori invariants. Unfortunately, these are like manifolds, Zn manifolds, so you can't represent all the homologies. So then the hope was that these a priori invariants are it. They're the rigid part of the obstructions. That was the hope, okay? Or maybe that was the hope. I'm not even sure that was the hope. It was that bold. It was too obvious. Because, yeah, you know, I don't know what this space is. So what is this space? So, well, I'm now divided by a half, and so I've got these groups 0, Z2, 0, Z, 0, Z2, 0, Z, and now I put it in the world of where I have a half, and it becomes 0, 0, 0. The Z becomes got a little half, 0, 0, 0, Z. The Z with a little half. 0, 0, 0, Z. So I have a space like this now that I want to study. And then if I put bot space here, Z2, Z2, 0, Z, 0, 0, 0, Z, Z2, Z2, 0, Z, 0, 0, 0, Z. I put a half in here, and I get 0, 0, 0, Z with a little half. Oh, it's the same. These two spaces might be the same. I kind of don't remember the order of ideas here. Let's see. Yeah, I think, okay, I think, yeah. I kind of forget the chronological order of ideas now, but I think I actually knew these two spaces were homotopy equivalent before I understood the obstruction theory. I forget why now. Oh, well, anyway, the idea is that they're both related to Bourdism. Namely, consider the homology theory, where you define cycles by maps of oriented smooth manifolds into the space, and two are equivalent if they're covariant. And you get this Bourdism theory. And then I'm going to tensor it with a half, get rid of the two torsion. And then there was a famous theorem, I remember now. So Connor Floyd came to Princeton and gave Connor or Floyd, I forget which one, maybe it was Floyd, came to Princeton, gave a lecture, and they proved a theorem that when you take complex boardism and you tensor it down over the integers with a certain genus called the Todd genus, then this becomes complex K homology. And well, I can do that. So now with this half here, the theory looks a lot simpler. You can take this mod, you tensor this down over Z bracket a half with the L genus, which measures the signature. And then I just copied their proof from the lecture, and I could prove that this was KO homology with a half. Okay. So this is Connor Floyd, and I don't have time. This 1967 book on the relationship of boardism and K-theory, and this is a variant of their theorem.
Say it again. So the first one is?
What?
How is it the first one? The dot.
This one?
Yeah.
Yeah, so what this is complex boardism, stably almost complex manifolds, and there's this homomorphism into Z called the Todd genus, a certain combination in some formula and characteristic classes C1/2, I don't know, maybe there's a 12, the next one, I don't know. Some formula in terms of characteristic class. Do you know the next term? What is it?
1/12.
What?
It's 1/12.
112 C2, okay. Anyways, a certain formula, and it turns out it sends, when you apply it to a manifold, well, when I say Todd genus, then you take the component in degree, in an appropriate degree, which is the next one will have C3 and C1, C2 with rational coefficients. They'll be polynomials, they're called Todd polynomials. You evaluate them on a manifold, and it turns out they give integers. Because it's the index of the Dirac operator, so that's why it gives an integer. So, and then this homology theory is a module over the manifolds. You could cross with any manifold and project it back onto here and then go on in if there's a module structure. And then you're tensoring this module over the groups of a point via this homomorphism with the integers. That's what this thing is. And then they prove the remarkable fact that this is a homology theory, and then from that there is already a homomorphism from it. Now this map here is given by a map from boardism to K homology. There is a map like that. There's a certain vector bundle construction you can make that gives the map. It's the exterior algebra. And anyway, then you process this map. It's like some might call it a Todd map or something. This was all floating around and very much in the air because of the Atiyah-Singer index theorem. Atiyah-Singer index theorem says the indexes of operators, Dirac operator with coefficients in a vector bundle B over manifold M is given by this integral. So Connor Floyd had this, so that was great. So I could prove the analog just by following their proof, essentially, real K theory. And then this L genus here is basically the signature. But see, this Z that I have is the signature divided by 8. And I'm in the world of odd primes. The 8 doesn't matter. And so I use the fact that I have the surgery obstruction, which is also related to this, and I can work out a proof that these two spaces are the same.
I'm confused about something. Are you saying that the K theory with 1/2 inverted is the same theory as the prior Eilenberg-MacLane spaces?
No, that was at the prime 2. So that was all at the prime 2. I had to use odd multiples.
Oh, that was at the prime. Okay, clear.
Right, that was at prime 2.
Right.
I'm using
I'm
Tom's
sorry.
here. No.
Yeah.
I don't know at all what this space is.
Got it.
So George Cook's answer does not
help me at odd
That was
primes.
Answers it perfectly at the prime two.
Okay, understood.
So I got this space, but they both are related to the signature, let's say.
Okay.
I can take the Counter-Floyd theorem and do a
Right,
signature
right.
analog. And, well, let's say somehow I'm going to prove, I forget the exact order of ideas, but, so that's not enough. I mean, so Steve, I could still come around and say, well, how do you, if you have a vector bundle, these are the homotopy groups, you get a sequence of obstructions that trivialize a vector bundle, how do you compute those? See, that problem was around already. How do you compute those? Now, I didn't know that that's not something you can do. So, the next thing was to say, turns out when you put a half in, complex K-theory is two copies of real K-theory, so these two theories are the same in the world of a half. They're equivalent. So there's no question, because complex conjugation splits it in the world of a half into two pieces. So these two theories are the same, and this theory is the same as that theory. And so we really are down to the question about K-theory. The classifying space for manifolds of the homotopy type is a K-theory thing. So how do we? So there is a theorem that go like this. Suppose you have the homotopy type. It satisfies Poincare duality. Poincare duality. Turns out you can ask that it satisfy Poincare duality for any homology theory that is multiplicative. So, I guess using this fact, so I guess there's a theorem that any PL manifold is orientable for KO hat. So that means orientability means there's a cohomology class that represents a generator when you look at the neighborhood of a point around the boundary. There's a cohomology class that restricts the generator here. That's what orientability means. So there's a statement like that for K-theory that there's a class which is a generator, and then you have Poincare duality. You have Poincare duality in KO theory with a half. This is for any PL manifold. Now this was known for smooth manifolds, and you make a star construction of the element K theory and relate to the L genus, and you need a half because when you restrict that to see whether it's a unit or not, it's a power of 2 times a unit. It's not really a unit, but it's a unit in the world of odd primes. So you have Poincare duality trying that was known for smooth manifolds, and then that argument can be extended with these surgery instructions to PL manifolds, and now it becomes decisive. So the theorem is, because the maps, we're talking about maps into, so the theorem is that this gives a bijection. There's a bijection between the manifold structures on X and the units of KO half a half. So in other words, the different, see, in ordinary theory, there are only 2 orientations, because the appropriate group is Z, and it's got these 2 units. But here we're talking about K theory, the ring. So it turns out 2 orientations different by a unit. And so this is in odd primes. This is, so that's the theory. Yeah. So, and you also get that it's even better that if you have a homotopy type and you don't know whether it contains a PL manifold, then you have all these obstructions for doing that. It turns out in the world of a half, the obstruction is precisely the k-orientability of the homotopy type. So the homotopy type in the world of a half contains a PL manifold, where these obstructions all vanish to get in a PL manifold, if and only if it's k-orientability, k-orientable, and then the different k-orientations, which you just take one and multiply by a unit, they give you the different structures. That's the theorem. That's what the title of the talk means.
So the right-hand side naturally acts on the left-hand side?
No.
Is the bijection?
No, this is already, yeah, but see, well, given an orient, let me say it correctly, K all orientations. The structures here are, so this is acted on by a group of units. This is acted on by a group of maps into that space. That space is the classifying space for K-theory, but the ring structure is the potential product. Ring structure of K-theory.
So this is for simply connected.
Yeah, something like 5, 6, 7.
So, if I
Pi
might,
primes.
so to understand that orientability statement for PL, at least for smooth, is that simply the statement that every spin manifold is K-orientable if they invert by a half?
No, that's not the right way to look at it.
But would that be a way? No.
Well,
when you invert a half its spin, you get rid of the spin. It's basically all SO, and so any SO orientable manifold has a spin structure that invert a half.
No, but see, that construction uses the spinor representation.
Right.
But I can just take a smooth manifold and just take the differential forms and use the star operator and build an orientation.
Okay.
That will have genus, the L genus, and it will be 2 to the n times the generator for every smooth manifold.
Oh.
That one is the one that extends to all PL and topological manifolds. So it's much more robust.
Right. I was just trying to
No, I
put
know
together
that.
my intuition.
Yeah.
Why that should be. But I understand your point.
See, well, if you say it, okay, let's talk about it. Because there are 2 things to say. One way you look right, one way you look wrong.
Okay.
Dennis,
Yeah.
if you tensor omega SO without inverting, with Z without inverting 1/2, you don't get a homology theory.
This one?
Yeah.
I wouldn't know. Oh, wait. You would know. I mean, you would know, but you don't care, though, because, you see, this theory, SO at the prime 2 is a collapsing theory. It's the sum of ongoing plane spaces, so you can analyze any question. I mean, you don't need to know. I mean, it doesn't have to be this is the right statement. You know the structure at the prime 2 anyway. So that's the best answer, I say. I mean, you'd have to see that. I mean, even knowing the ring structure of a group of a point is beyond me at the prime 2. How all that works, you know. So I don't know what this is.
I was just wondering if you possibly could get the L.
No, but I can
L
make a
theory
homology theory where I put Z. I can make this become a homology theory.
And is it the L theory?
No, not at all. L theory is the name for surgery theory. Because it wouldn't necessarily have these E2s there. In fact, in those days, this is driving a T in nuts, because if the index theorem was like magic, any invariant could be encompassed in the index theory. You couldn't get those E2s. It drove him nuts. Just kind of enjoying it. Because we could actually, topologists, we all had beards and long hair and stuff. Analysts were more neatly dressed, like Trump and anti-Trump. So we could prove any theorem that you could prove with the index, any theorem you could prove with the TSC index theorem, you could prove just using this surgery theory type stuff, except if it involved the prime 2. And a lot of interesting theorems do involve the prime 2. But these theorems all extended to PL manifolds and everything. So, but the prime 2 has its own flavor in the category of manifolds as it does orthogonal. I don't know if that's been changed. They've done it yet. Now there's one more point I'd like to fit it in before we stop, which is, so this is kind of an answer, sort of. I mean, it's a nice conceptual answer. So a manifold at odd primes is a K-theory orientable object. And PL manifold at odd primes, and at prime 2, the PL manifolds are, you can break them down into cohomology classes, so you understand that too. Okay. But this theorem does not answer the Halper-root question. See, how do I know this is a topological invariant? It involves all this torsion information. Novikov just proved the rational part of the topological invariant. So that's where Pontryagin duality comes in. So this is Pontryagin duality. I was talking about this morning. Let me do it for odd primes now. So think of putting an odd prime here, and then this is E mod P. I put maybe P squared here and P squared here. N is P squared. And I've got a homeomorphism, and I know that all the obstructions that are a priori by Novikov's argument can be shown to be zero. And I do the transversality on Novikov and then calculate the surgery obstruction. But there are all these homology classes that can't be represented by manifolds. But then I'm hoping that the obstructions will be malleable, cooperative, and can be changed. The rigid ones are all coming from K-theory. So I can use the homeomorphism. So this doesn't do it, but there is this neat thing. Read cohomology theory here. You can have a K here. But anyway, if you have a cohomology class with Z mod N coefficients, you can get a homomorphism from homology with Z mod N coefficients, Z mod N. And this is an isomorphism for all N.
That's for any cohomology theory?
No, never.
Okay.
For ordinary, it's true.
For ordinary is what you say.
And this is a 66, and it was a big deal to use this telephone. I was in England. I called up Attia. I don't think I even knew him. That's for Attia. I think he got his Fields medal. Yeah. So you can still talk to him. No. So does K-theory, so I call this Pontryagin duality. Does K-theory satisfy Pontryagin duality? So the K-theory would, that's what you just asked. He said, no, that would imply infinitely fast mind starts working, and he said, no, that would imply this, imply that. No, I don't think so. I said, okay, thank you. I called up Adams. He's in Liverpool, this is in Oxford, I was worried. That's also a big deal, you know, but still in Texas we just call people on the phone. Professor Adams, does K-theory satisfy Pontryagin duality? Silence. I don't know. Good. So then I started asking other people. Anderson was around. He sort of explained why this was a homology theory to me. And Luke Hodgkins explained, KO does not satisfy this because for this to be true, these groups have to be Zn modules, and KO with Z2 coefficients as an element of order 4. So it doesn't satisfy this. Anyway, but all those obstructions go away if you have a half, and you can actually prove that in the world of a half, KO satisfies this. Okay? Then we have the Connor-Floyd theorem that the K, now we put K here. We have the K homology is given by these things. These are maps of manifolds in, and you can do Zn coefficients, and they're maps of these manifolds with pages going in. And then I have my a priori obstructions. And I can use Novikov's argument to show there's zero, which is a homeomorphism. And so I get that the image over here is zero on my obstruction. Well, that takes care of the odd primes. So, see, that's nowadays people don't even realize that's a hard theorem because it's trivial to prove. But, you know, Tia thought it was false and Adam didn't know. And Anderson and Luke Hodgson's weren't so sure, and so on. They told me things, so on. So anyway, so K-theory not only does it organize the structure of manifolds at odd primes, but it actually, because it satisfies that property, gives you a set of a priori numbers to compute. And then when it is a homeomorphism, you can use Novikov's argument to show there's zero. That was it. Just in 1967. I'll stop. So that was a good question, Steenrod. I really appreciate that. Although it pissed me off at the time. They want us. Any questions?
Yeah, Mahmoud's question about what's going on if you just took SO and tensor over L with Z. That would kill the Z mod 2 parts in SO, because you can't, you know, have Z2 acting on Z. But so it's still possible because of divisibility, I guess. That you know that if you invert 1/2, what you got left over does give a homology theory. So how would it violate, let's say, the long exact sequence axiom? Something might multiply by a power of 2 that doesn't fit the long exact sequence, or?
It's not the right question.
In
the sense that, you know, we know, oh, so it's here, right? We know this thing exactly. I mean, modulo computation of what the ring is. So, and it's the sum of ordinary cohomology theories. So, I mean, you know, it could be, you can modify this. You can change what L means and map it, get something that works a little better, and I don't know.
I think there's some theorems that if you prove.
Oh, I see. We're not having this because this at the prime 2 is different from this. At the prime 2, these two sides are different.
Right.
Yeah. So,
I think Hopkins and Hovey said if you did omega SP tensor
that works.
with Z, that will work and give you KO.
Yeah, that works. So, omega spin tensor over, they call it the A hat genes, but this has some Z2 information in it with KO of a point or something. I don't know how you have to write the right groups here. Yeah, it's KO of a point.
Right. Gives you KO theory.
Right. That's true. Well, this A hat is not just the Z part, but has some Z2 parts, so that's true.
And that's like Hopkins and Hovey proved.
Yeah, Hopkins. 80s.
That's a good question.
This is hard.
Yes.
And Connor Floyd have done earlier, and it's not hard, but I think this is the natural one. I don't think this one is useful. It's useful for what it does.
Right.
You know, but it's not in this scheme of genera and so on. This is symplectic tensor over, again, some kind of A hat, like the same thing. This is symplectic K theory.
Right.
And this is the Pontryagin dual of real K theory. Yeah, this is the Pontryagin dual, as I was explaining this morning. So this is the better one. This one won't have this feature. Mm-hmm. This will have this feature. There'll be invariants that you can use to tell what's going on. Well, this is not a very user-friendly talk, I think, for some of you, but So my thesis was the prime 2, and then this is what I worked on in the next year. That's the following up. And I left the field. Thurston, I met Thurston. So there's stuff to do. Let's see, there's nobody, the 2 young people had to leave. The stuff to do is this Pontryagin duality, which plays a crucial role in the algebra thing. So let's go to now smooth manifolds and structures and so on. The thing to do is, well, like the Wednesday seminar, last year you had a lot of fancy stuff about elliptic genus, things like that. I mean, these are all the A hat and T and L are all special points of that story, right? And there's one kind of global thing. And I kind of know stories here for T and for L, and sort of, if this one works, I can guess a story here. And I don't know what the story would be for that combined object, but the idea is that when you have objects that are defined locally somehow, and they have some algebraic topology meaning, like cycles, or cycles with boundary, then you can plop on top of it this algebraic theory of elliptic genus and so on. And that's the Bourdism. Now the physicists have a lot of Bourdism type things. They have what they call the bulk, and then they have the boundary, and they have quantum field theories going on. They're kind of calm here, and they're more agitated on the boundary. And, you know, and they have all this stuff. I sort of feel like some differential geometric information is required to describe the quantum field theory. In this context, can be sort of Bourdismized. You know, these are boundaries, filling ins, and you can do this genus and elliptic genus as a kind of invariant, and those might be the important. I think on Wednesday I have putative condensed matter physics, so I'll say how that story goes, but I only understand it in this case.
So you have some idea what theory you might try out.
Yeah, I don't know anything about it. I don't even know what these theories are. I can't understand it. But
Okay.
it's just, it has the flavor of what goes on. See, what goes on here is that something is defined kind of locally, the idea of a manifold. And then you use that in this homological way to build this algebraic topology. So I'm thinking you could also use other, physics is local. I mean, the phenomenon they measure in laboratories is local.
Well, and quantum field theory is based on locality.
It's based on locality, right? Exactly. So, you know, whatever we have in math, it should be encompassed by one of these local theories. So,
Right, because there's local, right? There are theories that give you the genus.
Yeah.
So the idea is that your thing, maybe if you modify, you would somehow start seeing things like your omegas and k's.
yeah. Well, these are like the
Or
these
omegas.
omega. Yeah, these omegas are going to be like these manifolds and manifolds with boundary, where the theories exist.
Okay.
You know, they're space-time is a manifold, generalized. But this is kind of miraculous, this algebraic topology here. It's really miraculous. I mean, Bott's theorem and the integers and these things give integers, you know, the integral. See, yeah, that's why I like to state the way I did this morning. De Rhom's theorem is any homology theory, let's say it has finite type over a point, when you tensor it with R, is just canonically isomorphic to de Rham forms on the space, but with labels. So you don't just take one form, you take collection of forms with labels. They're labeled by the groups of a point. It's like a function from the homology groups of a point into the forms or something like that. And then that's your generalized form. You take B and so on, take homology, and that's isomorphic to the whole theory. So a lot of physics, and then you had the theory itself over Z. I'll just emphasize the theory itself over Z maps into here. So you have these vector spaces, and you have a lattice in them, given by the image of the integral part. You also have the lattice. This is also equivalent to theorem theory, which is ordinary cohomology with labels. So it has the integral lattice of integral cohomology, integral homology. But that's not the same lattice. Mm-hmm. It's very important in degree 4. In fact, it's that same 2 I had a twist here. In dimension 4, they don't use P1, they use P1 over 2, which is not really an integer. But it is, if you think of it in K-theory, it is an integer. See, so a quantum theory often has some, first of all, it's described in terms of differential forms and tensors and actions and connections and stuff like that. But then it has some quantization conditions. Certain things are integral. And I think, well, Dan Fried could probably give a proper discussion of this when you get him to come and tell. But you can imagine that there's just the right, for a given theory, there's just the right cohomology theory that gives the right lattice for their quantization conditions inside the real stuff, which is what they're writing, because they're writing everything in the continuum model with differential geometry in mind. So they have all the real stuff there, but there's some quantization conditions, but it's given by, presumably by the correct cohomology theory. And then there's a way to combine these two things, to combine a theorem and the cohomology theory to get what's called differential cohomology, and that's this final product of this diagram. And that also seems to fit very well with some of the discussions. So I think, you see, the one I was doing was just sort of out of the blue. I mean, if you're a differential geometry and stuff, you don't know from PL manifolds or anything like that. And yet, you go over here, it's a completely different discussion. There's no linear algebra, no nothing, there's just geometry. And you get a copy of K-theory in there. You know, with all this stuff. So, but what was happening here is that you had locality. You understand what the manifold is like locally, and that is geometry enough to do the cutting and show it to homology theory. So these defects in quantum field theory, I don't know, it's a vague thing, I can't even formulate it. I see there's, this discussion is not completed yet, even though it's 50 years old, it's not completed. This Pontryagin duality here hasn't been written down and clarified. Elliptic genus hasn't been clarified in its further ramifications in this case, and so on. Basta.
So does the
Shagan. Shagan for basta. This is Italian for enough. Ça suffit.
In the definition of original definition of elliptic cohomology, they also have to invert 2. So
they don't always have to.
You don't have to anymore.
Huh?
There's an extension of it with 2, and 3 do not have to be inverted.
Yeah.
But let's say you invert 2.
Yeah.
You can ask whether it satisfies Pontryagin duality or not.
Yeah.
Because for a particular elliptic curve, it does, right?
I don't know.
I mean, because those are special point. The special.
Oh, those special point elliptic curves too.
Yeah.
Well, my student who had to leave, he's my expert in this. I'll ask him.
I mean, there are 2 parameters, delta and you know, there are two parameters, and you can
Delta and epsilon.
fix them to different things so that it gives you the signature.
Yeah.
So in special values, it gives you this example, which is KO.
Yeah.
K with 2 inverted,
Yeah, with 2 inverted.
because you get the
So one concrete question would be, does that satisfy occurring duality
And that being,
with arbitrary delta and epsilon?
oh, I see.
That's a good question.
What is a group point?
Well, it's
What
the
is the coefficient ring? What is it?
free ring over those generators.
The free ring?
That's without having assigned it any special value.
Right.
Right, yeah.
The free ring of those two generators if you invert 2 and 3?
I think so.
Oh,
Right.
yeah.
You get modular forms, actually.
It's basically the modular forms.
Right.
Well, there's this naive housekeeping thing you have to have. Let's see. Well, first of all, you have to process it to make it go in positive and negative dimensions.
Yeah.
You have to do that. You probably have to invert those two generators.
You actually inverted what's called a discriminant.
Yeah, you can.
And that's
Just invert the discriminant.
You inverted, and that's why you have to have 2.
Otherwise, you won't get a cohomology.
Right, exactly.
What the grading of the discriminant?
I think they are in degree 12, is it?
12, yeah, because the delta's in degree
4.
and
One is in
epsilon's-
degree 4 and the other one in degree
So
6.
it's epsilon squared times
So
delta.
where's the thing you invert? What degree is that in?
12.
12.
I mean, there are different choices. There are 3 different choices you can have to invert.
Right. And it was
You can also invert like one of the.
But you have to have this property that when you invert, we reflect the groups of a point. First, you have to make them go in positive and negative dimensions because you know. So I'll say the property, and you'll see why anything that's in positive degrees is never a contrary dual. Degree 0.
Yeah.
And that's the property is you take its mirror image, and then you have these two things. So if it had stuff in positive and negative degrees, the mirror image might look kind of like the same thing. Right? And the homology, if you think of this as the homology of a space, this has to be the cohomology of the space. So that takes care of the torsion. If there's z's, the z's have to be in the same place.
That's a necessary condition. It's like
That's
checking it for a
necessary
point.
That's to even get started. And then if you had a map that realized that, then it would be an isomorphism at a point, and then get their cohomology theories. Yeah, and there are cohomology theories for these things, I think. If you use the construction I did talk about this morning. Yeah, that'd be very interesting to find out. But you have to do this, you have to make it satisfy this symmetry. You just do it rationally first. So you have to do something to make it look symmetric under the mirror. Right? So K-theory is already symmetric. Real K-theory isn't. But when you shift it, it works. Amazing.
Do we applaud the Einstein chair
Yeah.
speaker?
I had a slightly better reaction from you than I did 50 years ago when I was trying to explain this stuff to my colleagues. They're all geometric topologists. They didn't want to. Plus, it was much more abstract. It was the Adams operations and the p-adic integers and the Deli's Galois group and localization and completion and Tall theory.
So it took you,
It was just sitting there.
so it took you half a century to find the right audience.
What?
So it took a half century to find the right audience.
Audience, right. Much better than this. There's this poor guy in dynamics. All this stuff.
Very, very